Okay, so a very confusing concept. Asymmetric centers, stereocenters, chiral centers. How to be able to very easily identify them. First, let's introduce what is asymmetric center. So asymmetric center, it is just a tetrahedral atom that is connected to four different substituents. You have four different substituents that are connected to the same atom. We call this an asymmetric center. It looks like this, something like this, with four different substituents. It's like here, 1, 2, 3, 4. These are four different substituents. This is called asymmetric center. This asymmetric center is the same as chiral center. So asymmetric center and chiral center are the same thing, because a chiral center, again, it is a tetrahedral atom connected to four different substituents, 1, 2, 3, 4, to the same atom. It's called chiral center or asymmetric center. So we have another concept which is called a stereocenter, or people call it sometimes a stereogenic center. What does that mean? Well, there is a definition for stereogenic center, and it says it is a center or a carbon. It's in a molecule, and that is substituted in such a way that a new stereoisomer will be produced when two substituents on the same carbon atom are switched. It's like this exactly. So if I have here the same thing here, like this, and if I have this, 1, 2, 3, 4, if you switch any two substituents like 1 and 2, you will end up with this molecule. And these two molecules do not equal each other. These two molecules are isomers. So switching any two substituents on a stereocenter will result in a new stereoisomer. So switching any two substituents on a stereocenter will result in a new stereoisomer. And these two are non-superimposable. And because of their nature as non-superimposable, they are as well called chiral centers. So any asymmetric center is a chiral center, and as well it is a stereocenter. But then there is something very important that we have to be aware of. Stereocenters, we said any two substituents on a stereocenter, when they are switched, they will result in a new stereoisomer. So check this out. If I have this alkene, and I have here bromine, hydrogen, and I have here hydrogen, bromine, well, this is now just a trans alkene, right? What would happen if I switch these two? Well, you will actually have this alkene if you switch these two. Well, I didn't touch the left hand side. The right hand side, you'll have bromine, and you will have H here. Okay, and now this one is the cis isomer. So by switching two substituents on this center, I got a new stereoisomer. If I do the same on this one too, I'll get a new stereoisomer. So this center then is a stereocenter, because it is a center at which if I switch two substituents, I will get a new stereoisomer. But hang on, we said stereoisomers are chiral centers, and this is not connected to four different substituents. This is the major difference now. Every chiral center is a stereocenter. What is the chiral center? It's a center connected to, or a tetrahedral atom connected to 4 different substituents. But not every stereocenter is chiral. Remember, not every stereocenter is chiral. Give me an example. Here we go. Like alkenes, if you go between cis and trans, when you switch these two, you will get a new stereoisomer. And this carbon here is not connected to 4 different substituents, right? It is only connected to 3 different substituents. However, when you switch 2 substituents, you will get a new stereoisomer between trans and cis. You switch these two, you will get another stereoisomer. So every center here is a stereocenter. So this is the rule that you really need to be aware of. Every chiral center is a stereocenter, but not every stereocenter like here is chiral, because chiral centers must have 4 different substituents. So I always do it this way. I draw a big circle and I call this here is the stereo center, and then I draw another circle inside and I call this is the chiral center. So every chiral is a stereocenter, however not every stereocenter is chiral. Remember it this way. We just mentioned that by switching 2 substituents on this center, if you have 1, 2, 3, 4, by switching 2 substituents like these two, you will get a new stereoisomer which is not equal to the old stereoisomer. So if you have this 1, this 2, 3, and 4, these two are not equal. What would you do about naming? We will need a new nomenclature system to be able to assign names to these asymmetric centers or chiral centers. And then we will have to use the CIP rules naming system, which uses the RNS configuration and assign the RNS configuration to each chiral center. And how does it work? You go to a carbon that has 4 different substituents, which is a stereocarbon, or a stereocenter, or a stereogenic center, or a chiral center, or asymmetric center. All these names apply to the same thing. And you start to assign priorities to each substituent on the chirality carbon using the following rules. Number 1, you will compare the atomic number of the atoms that are attached directly to the stereogenic center. So you're going to use the atomic number of each atom directly connected to the stereogenic center. And you will use the highest number. The highest atomic number will have 1. So 1 will be the highest atomic number. 4 will have the lowest atomic number. If there is a tie, what would you do? Let's say the first attachment to the same stereogenic center is carbon. You will have to go to the other atom next to it. So go to the next atoms that are 2 bonds away from the stereogenic center. So you'll have to go to next atoms until you find a tiebreaker. 3, you have to draw the molecule such that the lowest priority is sticking into the page and the other substituents form a steering wheel. They count 1, 2, 3. So let's say you have this molecule. You will have to imagine yourself standing here, where the one that has the lowest priority is pointing away from you. So first, you have to assign the priorities to every substituent. Oxygen is the highest priority connected to your stereogenic center, and then this is a carbon, this is a carbon. So carbon, carbon, and then next one here is H, next one you're seeing is carbon because it's connected to another carbon. So 1, and this is 2, and this is 3, and this is 4. You're standing looking at the molecule in a way that making the one that has the least priority pointing away from you. And then you will just draw this steering wheel as if you're drawing a Newman projection. And then you have here the OH, you have here the methyl group, and you have here the ethyl group. And then you will just put the parities which you made before, 1, 2, 3. And then you go in a steering wheel this way. So remember one thing very important. If you are going clockwise, then it's going to be R. So if you're going this way, you will have a R configuration. If you're going counterclockwise, you will have an S configuration like this. So if you're going clockwise, you'll have an R configuration. If you're going counterclockwise, you will have an S configuration, such as this example. So this is S in that case. You have 1, 2, 3, 4. You go in this way. So this is S. You don't need to draw the Newman projection. This is just for yourself to be able to view how the molecule looks like. And it's a good practice for other cases for assigning R and S. So remember, you use atomic number. You give the one that has the highest atomic number, you give it 1. The one that has the lowest, you give it 4. If there is a tie, you go to the next atom on each carbon connected to the stereocenter until you find a tiebreaker. Again, the same rules apply to the next atoms. The one that has the highest atomic number wins. Like here, you have carbon and you have carbon. But this is a CH3, this is C2H5. So this carbon is connected to an H, this one is connected to another carbon. You always choose the one that has the highest parity, put it next. Don't choose the two hydrogens. Even though if you did this, this one is still going to win. But go for the one that has the highest parity as a second. So let's have some practice on these ones. Assign the R and S configuration to all the following molecules. Look at this molecule number 1. You will have to assign first parities based on the atomic number. First of all, this is my chiral center. It has 1, 2, 3, 4 different substituents. Perfect. Then assign the parities 1, 2, and 3, and 4. After assigning the parities, you have to ask yourself this question. Is the least parity group pointing away from you? If the answer is yes, this is the original case, where whatever you get, you do. 1, 2, 3, it's a clockwise, so it's R. Go to the next example. You again assign parities. First, you have to find the chiral carbon, and then assign parities based on the atomic number 1, 2, 3, 4. Ask yourself this question. Is the one that has the least parity pointing away from you? No. There are two ways. You either imagine yourself standing where the one that has the least parity pointing away from you, or in this case, if the one that has the least parity is a wedge, then whatever you assign, switch. So this is 1, 2, 3 like this. So this should be S. You're going to make it R. Again, so in the first case, if you have the one that has the least parity on a dash, assign it fine. In the second case, if the one that has the least parity is on a wedge, when you assign it, switch it. So this was meant to be S, but no, it will be R, because you are looking down the wrong axis, because the one that has the least parity is on a wedge. Go to the next example. Well, I'll try to find assigned parities, but is this chiral carbon? Well, it has NH2 and H dash and wedge. That's not necessarily true. The existence of dash and wedge doesn't mean this is chiral carbon, because you have here two similar substituents. So this one is not even chiral. There is no R or S for no chiral carbons. You're looking for chiral carbons only. Next example. Look for the chiral carbon. No, that one has 3 hydrogens. That one has 2 hydrogens. You're looking for 4 different substituents. This one has OH, H, ethyl, and something else. They are all 4 different ones. Okay, so this is my chiral carbon. Now assign parities connected to an oxygen, carbon, carbon, highest parity. Okay, carbon-carbon. Carbon-oxygen double bond is equal to carbon to 2 oxygens. So obviously this is going to be number 2. And this is carbon to a methyl. This is 3 and this is 4. Ask yourself the question, is the group that has the least purity pointing away from you? If you said yes, do it normally. 1, 2, 3. You're going counterclockwise. This is S. 5. Look for the chiral carbon. The carbon that is asymmetric carbon or stereocenter, and it's connected to 4 different substituents. This is what you are trying to assign RNS for. This is my chiral carbon connected to 4 different substituents. Oxygen is the highest purity, and now it's a carbon-carbon. This is branched carbon. This is normal carbon. Branched carbon is going to win over the normal carbon, and then 4 is the H. Now ask yourself the regular question, is the one that has the least purity pointing away from you? If you said yes, assign it normally. It is. So this is going to be S because you are going left counterclockwise. Going to number 6. Now look at this stereogenic center or chiral center. It has OH number 1, and now it has a carbon and a carbon. So this is carbon to NH2. So it's carbon, carbon, and then you have N, and then you have another 2 carbons, but this is the tiebreaker. So this is the highest purity now because it's connected to an NH2. And this is the 3rd, so, and this is the 4th, and the one that has the least purity is pointing away from you, so you are going normal, assign it, and it's normal. So this is clockwise, so this is R.